Hi. I don't know when you're watching this, but the day I'm recording this is St. Patrick's Day. So I will have my traditional pint glass, and I will do my best to tell this as if one was sitting at a bar hearing a story, at a pub, if you will. Let's get started in this unit, although it's the second lesson of the unit. I'm going to start off by playing a video. Write down what you need to. I'm going to mute the sound, though, because I can tell the story just about as well as he can. So you got a beaker here. There's just water in the beaker. The beaker's at room temperature. And a little bit of water is put underneath the beaker. So both are in the water phase. We add a little bit of this ammonium chloride. And we're going to dissolve it. And somehow through this dissolution process, some time passes, and then you've got some water under the beaker, and it's frozen. And it's so frozen that the beaker has now sealed itself to the block of wood. That video is probably older than many of the people watching it right now. And that has happened. So what's the story with that? This is something, if given a sufficient amount of ammonium chloride, you could carry it out at some sort of dinner table or at some sort of bar scenario. I'm going to dive in a little bit more to this process because there's something hidden there. So just to be perfectly clear about this whole process, everything was at room temperature. So you've got the water up here and you've got the water down here. To that, you add some solid at room temperature. But to tie this in with some stuff we've seen before, you know what happens when water turns from a liquid into a solid. I know what you might be thinking, and there's a certain rule of thermodynamics we're going to have to talk about in a minute. But you're saying, well, if this is an exothermic process, then my guess is that heat moved out of the water underneath the glass because it froze. And the only way it freezes is if it cools down. And if it cools down, it has to release that heat somewhere. So I'm going to guess that the solution at room temperature, the water and the ammonium chloride, as they mix, somehow magically it gets warmer. It has to get warmer as the heat moves up. Well, here's the thing. That's not the case. Because to suggest that would be to say two objects at the same temperature were now transferring heat in one direction. When two objects are at the same temperature and they're in contact, heat moves back and forth freely, equally. It's when they're at different temperatures that the heat transfer is unequal. If object A was hotter, you would see that more heat was transferring to B than was transferring back to A. The rate of the heat transfer gets equal as they're at equal temperature. There's no reason that temperature would magically move from room temperature to room temperature, making one colder and one hotter. We've talked about laws. Laws can't be broken. They just explain what happens. There's no except there. This means, logically, that there must be some process going on inside the beaker where heat is going in. So the only thing I can surmise from this is that if heat is moving this way from the wood and the water into the beaker and the solution contained, that something has caused the beaker to drop in temperature. Which is really strange because everything we're looking at is at room temperature. But maybe to make this a little bit more clear, I have another example with several different solids. Everything you currently see in this one screen is at room temperature, but we're going to watch anyway, and there's plenty of data this time.
When a compound is dissolved in water, it involves exchange of heat. This is known as heat of solution. Some of the compounds dissolve with evolution of heat. This causes increase in temperature of the water. This is known as exothermic dissolution. Some of the compounds require heat for dissolution. This causes lowering of temperature. This is known as endothermic dissolution. We will try out 3 dissolutions and see which of them are exothermic and which are endothermic. We need some water, sodium hydroxide, ammonium nitrate, sodium chloride. Note the temperature of the water. is 20 degrees Celsius.
Should hold on to that.
Add water to the first beaker and then add sodium hydroxide. Stir well. Note the temperature of the solution. The temperature is about 48 degrees.
What? That's like
Now add water
over
to the
100
beaker
Fahrenheit.
and then add ammonium nitrate. And again check the temperature. The temperature is
What?
8 degrees. Now add water to the third beaker and then add sodium chloride. Note the temperature. It is about 22 degrees.
That one I have problems with.
So we see that the dissolution of sodium hydroxide is highly exothermic. Heat is given out during dissolution. However, dissolution of ammonium nitrate turned out to be endothermic. Heat is required for dissolution. It is taken from water and its surroundings. Both these examples show a large exchange of heat during the dissolution process. On the other hand, in the case of sodium chloride, there is only a small change in temperature, indicating only a minute exchange of heat taking place during dissolution.
I like he just goes back to the computer. So, all right. So, like, I think I have an idea, right? I've got some bits and pieces of an idea here. So, the previous compound, the ammonium chloride, right? So, like, here, this is our sodium hydroxide. Here we've got our ammonium nitrate. Here we've got our sodium chloride. But our ammonium chloride, when it dissolved, I would have guessed maybe if you put a thermometer in there that its temperature was below zero. Like, clearly dissolving something into water, even though both the water and the something, the solid, the solute, are at room temperature, causes a change in temperature in the water. You can't have heat transfer without the heat coming from somewhere. Something that was said in the video, from or to the surroundings, heat of solution. There were thermometers involved, because now I can talk about this. There's no thermometer here. Ideally, you'd want to put some sort of thermometer in there so we can get our measurement. But hey, that person, the goal there wasn't to get calculations. The goal was to show qualitatively something. Now, what I will say about both of these is that no one's been very careful about measuring their water, because I know how to calculate energy changes in water. And I know that I need to know the mass. We would have to guess. But what I can talk about is that, here we need a scale, but the specific heat of water is fixed. As long as we're in the liquid phase, it's 4.184 joules per gram degree Celsius. And for delta temperature, well, now we can measure that because we have our starting value of 20. So for each of these salts, your delta T's would be something like 28 degrees Celsius, negative 22 degrees Celsius, and a positive 2 degrees Celsius. And remember what we said last time, exothermic changes would have a certain delta T and their Q, right? Everything's kind of negative for exo. Going out, leaving would be negative. So I like that. And in case you did forget that MC delta T, don't forget, it's always on that reference table. There's a QR code right above my head. We could measure, if we wanted to, the heat of the water. I want to make sure that I keep referring with these subscripts to water, because now there's this other component. Based on what we've talked about already before too, we mentioned that there's a relationship between the system and the surroundings. That any energy changes that happen, but the total energy changes that happen have to be zero. And that the heat, therefore, of the system is equal to the negative heat of the surroundings. And if you have an insulated container where you could measure, say, like, you get this cup and maybe make it out of styrofoam, and so it's nice and isolated from the rest of your environment, and you put a certain amount of water in it, and then say you dropped in, I don't know, some sort of block of metal, like, is there a silver here? No, I don't think there's a silver. We're going to make a black block. If you dropped in an aluminum block, suddenly in this isolated system where heat can't enter or leave, right? Styrofoam's pretty good about isolating from heat transferring. You can hold on to hot liquids in styrofoam. All of the energy gained or lost by the metal has to be lost or gained by the water. So this is a situation where we've got, a really well-designed system. We can use this equation, and we can start saying things like Q for the metal equals the negative of the Q for the water. And then, of course, anytime you write Q, you can plug in mc delta T. So if you know certain variables, you can make predictions about your final answer. This is called calorimetry, measuring heat. But what's weird here is we don't have a metal. You can totally measure the Q for the water. That's no problem, right? That's well documented. That we have a formula for right up here. The problem is it's not Q. There's no... If you're taking salt and dissolving it into water, you're turning solid into aqueous. I don't know what you'd stick a thermometer in. I don't know what the specific heat of a change is. So really we have to talk about something that isn't Q, but that's almost Q. Enthalpy is a term like Q that refers to a heat, but instead of talking about energy that's transferred because of a change in temperature, it refers to a change in some sort of internal energy. Specifically, enthalpy refers to changes that involve breaking making bonds or breaking making attractions. So when a solid turns into a liquid, we've seen this formula before. Q equals MHF. Well, that H there, we said was heat of fusion. This is an oversimplification. H frequently refers to a certain given arrangement. So you've got very poorly arranged waters kind of flowing all over your container. There's an H referring to the liquid phase. You've got nice, well-arrangement, solid block. You have the enthalpy of the solid phase. If you look at this process here, we're changing liquid into solid. We're changing H. And so here we would say change is always final minus initial. So solid minus liquid would refer back to this. Or if you want to say it more globally, it could refer to the heat of your products minus the heat of your reactants. And I'm saying heat, which is kind of funny. The two terms, heat and enthalpy, are somewhat interchangeable in chemistry lingo. That's why, I don't know if it's why. It may be a result of the fact that we chose H to represent enthalpy. So you'll hear the word heat a lot of times used, but what they mean is enthalpy. So you can also see this referred to as enthalpy of fusion. Frequently, you'll see things like this in different textbooks where it's M times like delta HF, because usually you don't talk really about the heat of a given state or arrangement. You talk about the change as a result of a process. This means we can bring things back to what we were talking about here. For ammonium chloride solid turning into its ions, our products are going to be a positive ion and a negative ion, which is stuff we've talked about before. We've heard that story already. But what we haven't talked about is there's an energy component to this. For ammonium chloride the solid, you've got your alternating ions, all like in that stacked, packed crystal lattice. For ammonium chloride aqueous, you've now split up those ions, so there's an energy change associated with that, and you're surrounding them with waters. So there's an energy change associated with that. And so there's a certain energy level associated with the solid phase and the aqueous phase, and rarely are the two energy levels before and after a process the same. Usually they're not. So that's where this heat comes in. Now we know from watching the video that this is an endothermic process. Now when it comes to measuring, everything I said before works. It all carries through. With one small addition. The heat for any system, if the system is the chemical reaction or the physical process that we're talking about, if this is our system, then we rewrite the heat of the system as delta H, because there's an H that refers to the solid ammonium chloride, and there's an H that refers to the ions split up in water. And in the case of you taking that solution, right, making that solution, putting the solid in the water, everything we also said before carries through. So we had said that the heat for the system has to be equal to the negative of the heat of the surroundings. With our substitution that we just came up with, delta H. So this is like something we can land at. We're like, we can use this now, because this means as long as we can design a controlled experiment where we can measure the Q for the surroundings, we can then back calculate what the delta H for the reaction is. And this delta H has all the same properties of the Q that we've seen before. So we had said on the previous lesson that, if there's a heat for a physical change, that heat could be represented by Q, like the heat of fusion, right? The heat is mass times heat of fusion. Well, all of those Q's would be plugged in for, like, if you want to put a number in your thermochemical equation, you could. Same thing with delta H. So if you know the value of delta H, you can also then come back here and start putting numbers in your chemical equations. I'll show you what we mean in a minute. So this here is a lot of information, and I know it's a lot to take in. So first, let's start with the word. Right? It says heats of reaction. Based on the second video we watched, heat, right? That correlates right back to the term enthalpy. And there's also a delta H right here. If you take a look at the breakdown of table I from your reference tables, there seem to be 3 sections. The first section up here generally show combustion reactions, where something with a carbon in it is reacting with something with oxygen in it, and you're making carbon dioxide and water as your primary products. There's 2 reactions there that are kind of just carbon dioxide. In the middle, we have a bunch of reactions that result in making one product. Synthesis reactions. Yeah, there's overlap, because we talked about that already. But in these reactions, that's just 2 reactants coming together to make a product. Frequently, the 2 reactants are elements, and the product is the compound made. And then at the bottom, we've got a bunch of these things that we saw the videos for in the first place, where you're taking a solid substance, adding it in surroundings of water, and making aqueous ions. So really, it's a lot of information, but it is kind of truncated and chunked off into parts that are a little bit more bite-sized. So there are heats of solution and heats of formation. That's the ones where you're forming just the compound from its elements. At the bottom, there's 2 footnotes that are like the most helpful. The first is that the delta H values in this right column, you'll see that plenty are positive, plenty are negative. The units at the top are kilojoules, not joules. So don't forget that 1 kilojoule is 1,000 joules. So these are some pretty large numbers, particularly that third one down, right? That's the reaction of octane with oxygen. That's frequently what happens inside cars. That's where we get, propulsion in a combustion engine. But you're talking about releasing 10 million joules, 11 million joules. That's insane. These numbers represent molar quantities represented in the equations, which I'm going to talk about on the next slide in more detail. And finally, in case you ever forget it, the reference table will always tell you in the delta H column, a minus sign indicates an exothermic reaction. If you remember, we said that Q for a system in a chemical or physical process is equal to delta H. That also informs what the sign of Q means. So you never need to remember it because it's always there. I'm sure with practice you'll start remembering it. In general, I do see all these reactions and like more reaction would release more heat, right? So not just talking about solutions anymore, but if I were to come up with a little bit more fun of an example. Here I have just a book of matches like you might get from a restaurant or pub or similar. But here we have wood, right? Again, we've got this wood, and there's some chemicals, some probably potassium chlorate, and some phosphorus on the matchbook itself. But everything here is in my hands. It's at room temperature. So if I strike the match, there we go. Obviously, heat and light are released. This is a combustion reaction, so we're turning our reactants into products. The wood is chemically reacting. Suddenly, we're releasing heat. It's continually releasing heat as I speak. the amount of heat that's released has to do with the chemical reactions occurring, but it also has to do with the size of the reaction. If I was burning a whole log instead of just a match, more heat would be released. If I was burning a toothpick, less heat would be released. So there is a component that says the more reaction that occurs, the more heat that gets absorbed or released. That means that for these reactions, these numbers, I don't quite know what they refer to. Well, that's what the previous statement had said. These are molar quantities. That is to say, the numbers that you see here are stoichiometric. So for this first reaction, delta H being a negative 890.4 kilojoules specifically refers to molar quantities in the balanced equation. That is to say, 1 mole of CH4 would correlate to negative 890.4 kilojoules. If there were 2 moles of CH4, if you doubled the amount, you would expect double the amount. And so on and so forth, and anything proportional. So what's kind of neat is we can add a layer to our previous stoichiometry. You can go from grams to moles to kilojoules if you're given that and that amount of that information there. The last thing I should say is, like I said, everything carries through. If delta H is negative, that means exothermic. And that means that heat is a product. So like I said, you can now add this 890.4 kilojoules into your chemical equation, making our thermochemical equation. I understand the confusion here, because if delta H is positive, then you write the heat on the right side. Sorry, the left side. If delta H is negative, you write your heat on the right side. But you'll notice that even though the heat is negative, I wrote plus 890 kilojoules. That's because in a chemical reaction, plus doesn't mean positive. Plus means and. Don't forget, if we convert this back into words, methane, 1 mole of methane plus 2 moles of oxygen yields 1 mole of carbon dioxide plus 2 moles of water, and, right? So it's and. So it's carbon dioxide and 2 moles of water and 890.4 kilojoules. So it's a little bit misleading, but you'd never really write a negative in a chemical equation. You need to know that when the number's written on the right side of the chemical equation as a product, that implies a negative delta H. So putting this all together, I mean, that's it. So I pulled out some reactions here. Let's take a look at some practice problems, and we'll kind of leave it there. That'll be a nice foundation for you to work on. For the first problem, that was that example we just saw. So how much heat in kilojoules? We're going to react 5 moles of hydrogen to create ethane. So I want to look at my list here, at my reference list. I want to find the appropriate reaction. There it is. This negative 84 kilojoules means that an 84.0 kilojoules is written as a product, just like I said before. Just to be clear, this 52 being positive would mean that a 52.4 kilojoules would be written here, just to make sure we're clear. But maybe we don't need all of this, because it's given me enough information here. We're relating moles to heat. So that would be that example that we saw before, our given quantity. And then we just have to go back to the equation. I see I'm going to do that and that. We're going to put moles of hydrogen on the bottom, kilojoules on the top. Just going to copy down the numbers from the equation. We've got a negative 84 kilojoules, and there's a 3 on the bottom. And then we just do our math. The moles will cancel. We'll multiply out. Negative 142 kilojoules, right, when we do our rounding. What I will say is the wording of the question seems a little bit vague, and I understand that. When you say released, do you need to say negative 142, right? This is hard, where chemistry and English meet. The word released implies that it's exothermic. So I will see, and I'm just communicating this to you, that sometimes people will say 142 kilojoules is released and they won't write the negative, but you need to know that translation in your head. That's why I always like leaving it negative. If you say negative 142 kilojoules was released, no one's going to look at you and go, so do you mean absorbed? No one says that. They understand, and so it's okay in this case to be a little bit redundant, to be absolutely sure that you know that negative means exothermic. But that's that example. For this second one, we're talking about, these solutions down here. Actually, this one, not this one. And we're going to do one of those calorimetry experiments where we've got 600 grams of water in a container. We're going to dump in some amount of potassium nitrate. We've got our temperature in there, and we're starting at 20 degrees Celsius, but some change is going to happen. So this is going to be one of our calorimetry problems, where delta H is going to be equal to the negative for the Q of the water. Now, the delta H in this case is kind of hidden in that practice problem we saw before because we're given an amount of potassium nitrate. It says half a mole. I'm going to shortcut things a little bit. All these coefficients are 1, so I think if half a mole reacted, we're going to get half this number here. So let me divide that out. And I also want to be clear that if we were to write this out, we've got negative of 600 grams of water, but we've got grams, and then the specific heat of water is 4.18 joules per gram degree Celsius. This is a little bit misleading too. There's like all these little hidden bits. Since this is in joules and this is in kilojoules, we have to like do a conversion before we can successfully solve these. Now, like I said, it's a factor of 1,000. Maybe we're getting to the point where we can do this in our heads a little bit. I better finish up. My drink's almost empty. But that would come out to be 17,445 joules once we divide by 2 and then multiply by 1,000. That is a positive because it's positive listed over there. So, and then finally, our delta T. Now, our delta T is always going to be final minus initial. We don't know what the final temperature is, but we're going to be subtracting our 20.0 degrees Celsius from that. At this point, I could let you go do the algebra. If you wanted, you could solve for the delta T and then go back and relate it to the 20. Personally, I like doing it this way because it is all kind of laid out and you see the thing you're going for. Let's do a little bit of algebra. Negative 6.95 degrees Celsius is equal to the final temperature minus 20.0 degrees Celsius. So we can add our 20 over. And so our final temperature here should be about 13.1. Let me look at my significant figures. It'll be 13 degrees Celsius. So this should be in line with what we saw at the beginning there, where if delta H is positive, the dissolution is endothermic. And since the water is your surroundings, then the water will get colder as the solid ions become aqueous ions. And it did. It went down by 7 degrees. So this all worked out. Thanks for watching.